What we're going to start with today, like I said, is exponential growth models, exponential decay models. We'll look at real-world exponential problems. And then tomorrow we'll look at real-world logarithmic problems. So the first thing, when we have exponential growth, we're going to deal with this equation down here, which is y equals a times 1 plus r to the t power. And when we're talking about a real life problem, we're going to be talking about a quantity increases by a fixed percent, during a fixed time period. And a fixed time period means like we have to establish how long it's going to take for something to happen. So for example, time period could be by hours. Hey, this is going to happen every hour, or this is going to happen every century. All right, but most commonly, the most common time period we're going to deal with is going to be years. That's just most common. But it could be hours, minutes, days, anything like that could represent the time period. Okay. So that's what exponential growth looks like. All right, and this exponential growth equation here, it could represent a few different things. Let's see, we'll start with saying the amount y of the quantity after t units of time. So we'll use t to represent time, okay? All right, and like I said, most commonly time is going to be represented in years, but not always. Okay, and then we have the variable r. That's going to represent our fixed percent, or our percent increase that represents growth. Okay, and when we do percent increase, we want to write it as a decimal. Okay. And then we have this variable a, which is in front of the parentheses. And the a, that represents our starting value. Or it's also the initial amount. Okay, those are some things we could see there. And then the last variable here is y. That represents the final amount.
What's 1 plus r?
1 plus r, we're going to talk about that in just a second here, okay? So this this problem here, this is just our exponential growth problem. You might see this if you're doing like bank accounts, like simple interest. This is the equation that you would use to represent that. All right. The key here is an interest rate like R. I said it's written as a decimal because, like, let's say we wanted to say 8%. If it were 8%, we don't want to put 1 plus 8 because that would be wrong. We want to put it as 1 plus 0.08, rewrite it as a decimal. The way you can rewrite anything as a decimal is you could take the decimal place and move it over 2 spots, 1, 2, and that would make this a 0.08 like that. Or you could do 8 divided by 100 because it's 8% out of 100%, and 8 divided by 100 is 0.08. So that's how you'd represent a percentage as a decimal instead. Okay, so really important that we note that. Okay, and what happens is we use this 1 here because the 1 basically represents 100%. And if you say, hey, we're going to grow something by 8%, what happens is 1 plus 0.08 is 1.08. And just like what we saw in the warm-up, this number is larger than 1. that's an example of exponential growth. That's how we can tell this is an exponential growth problem. You get a number that's larger than 1. The big key here is the plus. You get a 1 plus r, all right? Which is going to be, we're taking 100% of something, and then we're going to add another 8% to it. So that's why it's 1.08. It's like 108% of the original value, okay? And that's what 1 plus r represents. 1 plus r is called our growth factor. All right, and it must be larger than 1. Must be larger than 1. That's a fact about growth factors. All right. What happens is technically this equation here is y equals a times b to the x value, where b is the 1 plus r quantity. And we're just looking for the b value to be greater than 1. That's how we represent exponential growth. All right, so that's exactly what's happening with this equation. So it looks kind of weird, a little confusing, but that's the idea for this growth problem. Okay, so now our first example, using this exponential growth equation, we want to identify some key values here. So it says in 1996, there were 2,573 computer viruses and other computer security instances. 2,573, I'm going to highlight that in green because that represents our starting value. That's what happens in the year 1996. During the next 7 years, there's a time period, 7 years, the number of incidents increased by about 92% each year. 92% each year. Well, 92%, that should equal 0.92 if we rewrote it as a decimal. And again, remember we could do 92 divided by 100. That's the easiest way to rewrite it as a decimal. Now it says, write an exponential growth model giving the number n of incidents after t years, after 1996. So when it uses the variable n there, it's really just saying we're going to use n instead of y to represent our final amount. And t is still representing the time. So we can write this as n times a 1 plus r to the t. So we're using the exact same formula as above. We're just switching n and t. And now we can plug in some values. We don't know what the final amount is, but we know the initial amount of viruses was 2,573. And the rate was 0.92. And we're trying to figure it out for t years. So this right here represents our growth equation. If we want to simplify it a little bit, we could say, what is 1 plus 0.92? And simplify that part. 2,573 times 1 plus 0.92 is 1.92. And now it looks like that y equals a times b to the x, that exponential growth equation that we're used to seeing. All right, you can write it either way. Personally, I prefer simplifying it if possible to get this 1.92 instead of the 1 plus 0.92. That's my preference, but it's entirely up to you. Now, it says down here, use the model to predict the number of incidents in 2003. And remember, it says the number of incidents is t years after 1996. So technically, you'd say we're going to go from 2003 back to 1996. So we get 7. So the t value represents 7. Okay. So basically, all we're doing then for this part of the problem is we can say, let's start with 2,573 incidents. And we're going to say times 1.92 to the 7th power. when we put this in our calculator, we have to be very, very careful. Okay, you want to put parentheses around the 1.92, and you want to remember to follow PEMDAS. PEMDAS specifically. What do we deal with first? Parentheses. What do we deal with second? Exponents.
Exponents.
So we got to take care of our parentheses and exponents. A common mistake people make is they do 2,573 times 1.92, and then they try and raise that whole thing to an exponent. So you get a really wrong answer if you do that. What you want to do instead is 1.92 to the 7th power, and then multiply that by 2,573. So follow PEMDAS. What ends up happening is we end up finding our number of security incidents in 2003. 247,485 if I put that in my calculator. And I want to make sure to round that answer to the nearest whole incident. Round the answer to the nearest whole incident. It's impossible to have a fraction of an incident, so we'll just say, we're just going to say 485 incidents took place. Which makes sense, because from 1996 to 2003, there was a huge computer boom. People didn't have computers in 1996, but in 2003, it was a lot more common for people to have them in their houses. All right, even more so now. And also viruses became more sophisticated in that time period. So it makes sense that there's going to be some exponential growth pattern, and we go from 2,500 viruses to 250,000 viruses a year. So that doesn't seem unreasonable. What we want to do next is we want to use a graphing calculator, and I want to show you what it's going to look like on a graphing calculator over time. So just reminders that like when you're using a graphing calculator, you're going to use X instead of T. Because when a calculator, we're graphing, we're going to be in terms of Y and X. So we'd say Y equals 2,573 times 1 plus 0.92 to the X value. Or we could write it as the 1.92 if we've already done the addition. That's perfectly fine. All right, so I'm going to switch screens now. I'm going to put Desmos on so you guys can see it, and we're going to graph this. I would want to say, it says write notes about changing the viewing window and other information here. I'd want to say y-axis from 0 to 250,000 to represent the number of incidents. That's really the key, is picking an appropriate viewing window. You have to think about what makes sense. Now, the last question I ask here says, use the graph to estimate the year when there were about 125,000 security incidents. So what you do is you'd say, let's type in y equals 125,000 and then find the intersection. I'm not going to go back to my screen right now to do that, but you'll get a straight line like that going through your exponential growth model, and you'll look for that intersection, and the x value of that intersection is our answer. Okay, and when I plug that in, I will end up getting, I think it comes out to like, it was like 5 point something. So it should come out to about 6 years. Okay. So it says use the graph to estimate the year when this will happen. So if x equals 6, which is the same as like t equals 6, we'd say 1996 was year 0, and we're going to add 6 years to it. We get 2002. So in the year 2002, there were about 125,000 computer incidents. That's how we'd figure something out like that, working backwards. Technically, you could also use logarithms to solve, but I mean that's kind of tricky now that we know how to use logarithms. But if you can use the graph to do it, awesome. Use the graph to do it. That's going to be easier than having to solve using logarithms and everything like that. Okay, but that first example is an example of exponential growth. The key for identifying exponential growth, again, is the plus that we had up top at the very beginning of the problem. 1 plus r, because we're taking 100% of something and then we're adding another percentage to it. So it's going to be a number bigger than 1 when it's put together. Likewise, exponential decay is going to be represented by a minus instead of a plus. So exponential decay, r would represent the percent decrease this time. Okay, which we'd say, let's write that as a decimal. Again. And then this whole 1 minus r, that should be a number smaller than 1. That should be our decay factor. It should be between 0 and 1. That's our decay factor. The r and the 1 minus r. Same exact formula, you can do exponential decay. You can use this on your bank accounts, like simple interest on a bank account, if you're having fees charged to your bank account or something like that. Okay. And this time, we're talking about snowmobiles. You buy a snowmobile, anytime you buy a car or something, they generally lose value over time. So snowmobile costs $4,200 when you buy it. The value of the snowmobile decreases by 10% each year. Actually, you know what? I'm going to use green to represent the initial value because that was what our A value was before. So I'm going to do green again. Okay. And now it says, write an exponential decay model giving the snowmobile's value y in dollars after t years. So we can say y equals the A value, 4,200, and then 1 minus 10%. That's going to be 10 divided by 100, just 0.10. Okay, to the t value. There's our exponential model. Or we can say y equals 4,200 of 0.9 times t. I like the 0.9 because that shows me, hey, this is a number less than 1. That's showing me this is actually an exponential decay problem. So you might remember, hey, there's minus there. That's a decay problem. Or when you actually do the simplification inside the parentheses, that shows you it's a decay problem as well. But why 0.9? What's the 0.9 representing in a real world situation here? Can someone tell me what the 0.9 represents? Like, let's say after 1 year, you bought the snowmobile brand new for $4,200 and t equals 1 year. So you're just doing 4,200 times 0.9. What's that saying?
It's 90% of its value.
It's 90% of its value. Exactly right. So that's the 0.9. So we're losing 10% of value. So we have 90% of the value left. Okay?
So then if it was 2 years, then it'll basically be 81% of the value.
Exactly. So what happens after 2 years is it becomes 81% of the value because it's 90% of 90%. It's kind of a weird way. That's how this exponential growth and this exponential decay works. Okay? But if we're able to write a model, we don't need to worry about what the decimal is going to be after 2 years, after 3 years. We just need to know how to plug it into our calculator. So, for example, I'm going to use this 0.9 again to the third power because it's what happened after 3 years of depreciation. 3 years of time. Depreciation just means, by the way, losing value. That's an economics term. That's what depreciation means. So apologize for using that economics term if you're not sure what that is. Anyway, y equals 4,200 times 0.9 to the third power. So you do 0.9 to the third power, and it's going to tell you what's the new value after 3 years. And we get something that looks like this, 3,061.80. And I'm going to round to the nearest hundredth on this problem. Not because I was told to round to the nearest hundredth somewhere, but for a different reason. What does the 0.80 represent here in terms of money?
80 cents.
Cents.
Exactly, it's 80 cents. I'm rounding the nearest hundredth because we're dealing with money. That's the nearest penny. Always, always, always round to the nearest penny. Okay, whenever we're talking about money, even if it doesn't say what to round to the nearest penny. That's the key there. Okay? So anytime you're doing money, round to the nearest penny. Okay? So now, what we'd want to do for this one is we would graph it the same exact way. You do the y equals 4,200 and then the 1 minus 0.1 or the 0.9. You can do either one. And then you're going to use the graph to estimate when the value of the snowmobile will be about $2,500. This time, I'm just going to sketch it over here. We're not going to actually graph it on Desmos. You can if you want. I'm not going to open Desmos again and do it. Exponential decay is going to look like this. It's going to get closer and closer to 0. And then our $2,500 is probably going to be like somewhere over here. Whoops. Yeah, let's do it. We can do better at drawing than that. Starting at $4,200. Look something like that. And then the $2,500 would probably be right around here. And we'd be looking for that intersection again. Okay. I already know that it's going to be more than 3 years because after 3 years, you still have $3,000 in value left. Okay. And when I actually do graph it and look it up, I got t equals 4.924 years, which means rounding it up, it's going to be about 5 years before the value of my snowmobile equals $2,500. Okay. So that's exponential growth and exponential decay. Okay. Now the last thing we're going to talk about today that I think is super important, this is real life situations here. This is going to apply to pretty much everyone in this class at some point in your life. You're going to deal with what's called compound interest. All right. Does anyone know what compound interest is? Just the definition of it?
It's like
It's not.
it's percentage. It's like percentages that build off the result of the last percentage.
That's exactly right. Yes. So it's interest that's paid on two things. It's paid on both the initial amount and on previously earned interest.
Doesn't like the P stand for like principal or something?
Yes. So this is pretty cool. If this is good if you're like investing in a bank account or something like that, because what it's saying is like, hey, if I put $100 in the bank and next month it's worth $105, I'm not earning interest on just my $100 anymore. I'm earning interest on my $105. Okay, so it's your money working for you. So I made $5 after 1 month. Now I'm making even more money because I'm making money on top of that $5. Okay, that's what compound interest is. Now this formula looks really scary, but it's not too bad. There's only one new thing here. It's this variable n. Okay, everything else is the exact same as the formula up above, but this compound interest deals specifically with bank accounts. So we still see the p value is the starting amount. We're going to call it the principal in this case. Okay, that's why it's represented by the letter P instead of the letter A, but that's still the starting value or the initial amount. All right, the R is still the interest rate. All right. We'll call it the annual rate because you'll see something that's represented as an annual rate or an interest rate. And then the N is the new thing. T is still the time. The only difference now is that time is definitely going to be number of years. All right, so time with this compound interest formula will always be the number of years. And then A is going to be your final amount. And that's the same as before, just represented by an A now instead of the Y. And the new one, like I said, is this variable N. And what this represents is the number of times compounded per year. The key there is per year. So you could have the money compounding several times during the year. And that's what the N represents. So basically, if I said, hey, this is going to happen for T years and it's compounded twice a year, you would let's say 3 years. I'm just going to look at this real quick. Up here. Because if I say 3 years compounded twice per year, you would do 3 times 2, that's 6. So it's compounded 6 times total. So you would just run that interest rate 6 cycles. That's what the N times T represents. All right. And then we do the R times N because you're taking that annual interest rate and you're dividing it by the number of times it's compounded per year. And it's going to give you a slightly different rate. Okay. That's how this works. It's going to make more sense when we actually look at some numbers here. And we'll start with this first one. It says you're depositing $4,000 into an account that's going to pay 2.92% annual interest. And we want to find the balance after 1 year if the interest is compounded the following ways. It's compounded quarterly, monthly, daily, and every minute for the entire year. So we're going to set them up one at a time here. Okay, because it looks a little intimidating, but it's really not too bad. Okay, I just made up 3 years. That's where I got the 3 years from, sorry. So now on this one though, we're going to do 1 year for this example specifically. So we're going to say, hey, the final amount is whatever our initial amount is, 4,000 times 1 plus this interest rate, 2.92. If I divide that by 100, I get 0.0292. Over n, and then times n to the n times 1 power. Quarterly, like what does quarter mean? Like think about how many quarters are in a dollar. 4, right? 4 quarters.
So 4, yeah.
Yeah, 4 quarters in a dollar. So the same thing happens in finance. Like if you work, a lot of you guys are going to work for companies where you all the financial things or decisions are made by the quarter. So the year is broken up into 4 financial quarters. So you have 4 quarters in a year, which is pretty typical. So you would say change the n to a 4. The second example, same exact problem, but now compounded monthly, and there are 12 months per year. So you would change the n to a 12. But all the other numbers stay the exact same. Third problem, compounded daily. How many days are in a year?
365.
365. So you'd say 365 times 1. And then the last one's a little tricky because it says every minute. So if you want to do minute, you're going to say, okay, there's 60 minutes in 1 hour. There are 24 hours in 1 day, so 60 times 24. That'll give you the number of minutes per day, times 365 days in the year. That's how we'd find the number of minutes. And we're not worried about a leap year and 366. We're just going to keep it simple and say 365 days. So it turns out in 1 year, there's 525,600 minutes. And we would just, again, replace n with the 525,600 times 1 because we're only doing this for 1 year. Okay, now, what I'm going to ask you guys to do is practice putting these into a calculator or a phone or however you're going to calculate these. This is important because we're going to do this on the grade assignment on Wednesday. So we want to make sure we're practicing and doing this the right way. I'm going to give you the first one right now. After compounding 4 times in a year, you get $4,118.09 when we round it to the nearest penny. Okay. Answers B, C, and D should not be far off of that either. Practice putting the first one in, make sure you get the right answer, and then practice putting the other 3 in, and you should get answers that are similarly close. You shouldn't get an answer that's like $1 million or something like that. Because if you were making $1 million after 1 year, everybody would be doing that. Okay, so we're going to show you all of them in just a minute here. All right, but for right now, just go ahead and put them in your calculator and practice. All right. So it's $50 increasing by 10%. If I were to write this as a model, I'm going to say, okay, we're going to find the final price. So it's going to be represented by P after N bids. So if I were to write out the equation, we'd say P equals the initial amount, $50. It's a growth problem, so it's going to be 1 plus, and then the 0.1005%. If I did the 10.5% divided by 100. And then to the number of bids power. That's how I'd write this equation out. It's not a compound interest problem. The compound interest only works if we're talking about time in years. But in this case, we're talking about the number of bids. It's representing our timeline. Okay. It might be easy if you add those 2 numbers together. Like I said, it'll be easier to put it into your calculator. We can say 50 equals 1.105. And then I also see for a fact that this number is indeed bigger than 1, so it is representing growth. All right, what's the price after 5 bids? We can go ahead and put that into our calculator. What's the price after 100 bids? We'll go ahead and put that into our calculator. And then part D, is either of these predicted prices reasonable? Would you say that's a reasonable price to pay for the inline skates? Yes or no? So go ahead and put those into your calculator now and come up with your answers for your prices. And we're going to take a look at this in just a second here. For only those 6 bids or so. All right, so that covers a problem where you might see it being realistic for a little bit and then unrealistic after that. So just keep in mind what's in the realm of realism and when does it start to become unrealistic for a certain type of problem. Okay, and then make sure that your answer, does my answer make sense within the context of the problem? Like if I did this problem for 5 bids and got $12,000, first I'd want to recheck my work and make sure, did I do this correctly? Okay, and then if it does look like I did do it correctly, then $12,000 also seems unreasonable for a pair of skates. But at least check to make sure you did it correctly first, right? All right. with compounding interest problems, whenever you have an interest rate like 3 to 5%, if you start with $1,000 and end up with 15,000 after a year, then you probably did something wrong, because everyone would be putting money in the bank if they could make that much money that fast off such a low interest rate. Okay, so just keep those things in mind when you're trying to solve these types of problems. For your assignment tonight, just some practice here with exponential growth, exponential decay, those types of problems. Looking at problem 4 here, I just want to show you something. Anyone guessing, just looking at this equation, does this look like, based on our warm-up today, is this going to be a growth or decay problem?
Decay.
What makes you say that?
Because 1/2 is less than 1.
Yeah, the number in the parentheses, 1/2 is less than 1, which is exactly what this is. It's actually a half-life problem, which is like a chemistry or a physics problem that you might deal with. Something in science. I should say biology more so than chemistry. Or, I mean, more so than physics. But yeah, carbon-14 decays with a half-life of about 5,730 years. And the reason it's divided by 5,730 is because if you said T is your time, you'd say it takes 7,030 years to be exactly half of the amount it was before. Okay, that's what half-life means. All right, but that covers your assignment tonight. Best of luck. Let me know if you have any questions on it. We can look over a problem tomorrow on this assignment. No problem. If you want to stay on the call today and work on any of these problems, you're more than welcome to. Otherwise, have a great